After 50 years, we might conclude that everything's already being done just right in modern estimation. Reality says otherwise. Operational systems are subject to severe criticism for being years late, way overspent, and far short of expectations. Although many reasons contribute to that, some of our own shortcomings would cause significant problems even if no other shortcomings existed. We need to correct the effects of some past decisions that either were misunderstood in the first place or are outdated now. GPS vulnerability is exacerbated by forfeiting a ton of performance through loose coupling, but that's only the first in a long list of deficiencies, not in GPS itself, but in how it's being used. Coordination of surveillance with nav could have begun years ago. ADS-B has no collision avoidance capability without decades-old TCAS. Those and many more examples warrant urgent attention, with growing challenges from increasing complications, interference, and more traffic, whether manned or unmanned. Throughout this presentation, you'll hear many assertions that call for backup that time doesn't permit here. They're substantiated in the manuscript and in the 50-plus references cited in it. Before we get into the more subtle concepts, we can start with some easier ones. We know that although non-Gaussian errors are common, losing maximum likelihood is inconvenient but not disastrous. We won't go wrong with minimum variance. We're also familiar with the multitude of algorithmic capabilities we have that transfer function methods can't give, time-varying parameters being just one of many. Yet, to discard the frequency domain would be very unwise. Let's focus on one advantage of Kalman over a Wiener filter: optimality during transients as well as in steady state, but recognize that's contingent on knowledge of the covariance matrix of estimation error. The manuscript and its references show why it's necessary to forego that feature and how to use fixed parameter observers during initialization with unknown P0. Not fixed gain, but fixed parameter, which can accommodate variable update rates. Another attention grabber is non-Gaussian outputs from linear systems, even when all the input errors are Gaussian. So we can't mentally translate 3 sigma into an absolute value exceeded with probability of only 0.003. Even 10 sigma can't be completely discounted. One more item to mention involves the connection of block to recursive processing. Process noise loosens that connection, but later I show how to use it to facilitate an otherwise uncertain or laborious design procedure. Here's a mixed Gaussian example with values beyond 10 sigma. It only scratches the surface, but it makes the point mentioned earlier. The intent of SatNav IMU integration is widely appreciated, but not a lot of the ramifications. Some popular practices came along with the idea decades ago, but since then much has changed in both SatNav and inertial nav and in digital processing capability. Those practices haven't yet changed along with conditions. Now they need to. Also, state augmentation is used to excess despite causing observability problems. Virtually everyone includes accelerometer error states as if all 3 were separately observable biases. Only the predominantly vertical one should be included. Elaborate coning and sculling pre-processing should be for high-end IMUs in operations with demonstrated long-term free inertial capability only. Otherwise, coning is just part of the overall rotation drift, and sculling is adequately countered with attitude midway between delta V pairs. In addition to things being done that shouldn't, there are other things not being done that should. Usage of carrier phase ought to be more common. Here are some changes that have occurred since digitization, inertial nav, and sat-nav were all in their early stages. High accuracy and availability that we've come to expect couldn't be taken for granted in the 1970s. Inertial platforms were mechanically stabilized, so that gyros and accelerometers didn't experience large or rapid rotations. That's why their errors were smaller and less dynamic. So bias wasn't a glaring misnomer. That was then, this is now. Even for data averaging periods of a minute, inertial instrument bias is a glaring misnomer. How many times have you read this? Tracking is nonlinear, either in dynamics for spherical coordinates or in observables for Cartesian representation. Don't believe that. With a Cartesian model in stabilized coordinates and measurement residuals expressed in a sensor-based frame, nonlinearity effects are smaller than the random measurement errors. Now for some habits we need to break. Navigation and surveillance are largely separated due to old mechanization constraints eradicated by digitization. Integrity testing originally came with nav estimates that were suboptimal and therefore separated from the optimized navigation. Surveillance has forever been considered synonymous with position report sequences, with performance judged by position accuracy. I've shown a truckload of reasons why that's nowhere near adequate and why accuracy is needed in velocity far more than instantaneous position. So let's hit the nail on the head for just what we need for effective estimation. First, it's crucial to have a good choice of state variables. I wish we had more time here for dramatic examples of that. You would be astounded. Then, given a good state characterization, here's what the system needs for continuous observability. Subdivide the full operation into subintervals of duration equal to a data window. Within each data window subinterval, having enough measurement data to infer that brief state history, it's observable. Periods when that condition is not met call for further scrutiny. Watch the covariance matrix elements and also test residuals against their RMS values based on their sensitivities and on those matrix elements. Here's a basis for radically simplifying sat-nav inertial navigation. Updating with GPS GNSS interrupts the Schuler cycle, and it keeps on interrupting it. That cycle can't even get started, let alone completed. 84-minute periods don't describe performance with GNSS accuracies. Those propagation characteristics, shown in my 1976 book, were also based on accelerometer and gyro biases. Again, that was then, this is now. For multiple reasons, if performance matters at all, a major overhaul is in order. Not only tight instead of loose coupling, that's only the beginning. Even for 1/10 of the Schuler period, over 8 minutes, these simple equations are enough for the dynamics, applicable in different forms, with position states included or excluded in separate channels that can be combined into a full three-dimensional model. Continuing to use the old ways will, at best, spin wheels, making LSBs buzz back and forth from 1 to 0. Or at worst, make your program far less transparent, slower, and vulnerable to dozens of unmodeled inertial instrument errors, which the IMU specs don't cover in detail. Designers need insight to set the process noise spectral densities in the right way. Here's how. The manuscript includes a simple program relating error states to process noise for data window durations ranging from seconds to several minutes. Here I use the three-state model with velocity inputs accurate to 1 centimeter per second, which is validated with flight data and documented in my 2007 book. For this run shown, block and sequential error models closely agree for history of output velocity and the product G times leveling error. Then, dividing the latter by 9.8 produces an RMS tilt of only 3 microradians. You won't see specifications like that, nor velocity specs below 2 millimeters per second anytime soon. That illustrates why I've said over and over for decades, integrating satellite and navigation calls for a short-term dynamic model for error propagation. People often ask, why sacrifice the ability to coast free inertial over an hour or more? Well, that capability did not disappear. The state vector propagation in my 2007 book, for example, has all the requisite precision. The simplifications just described are for propagating the covariance matrix in applications involving sat-nav accuracies. Anyone who is satisfied with a nautical mile of error can obviously go with the older conventional methods. But if long free inertial coasts are required, be ready to spend for the IMU. Another question that arises about the approximations in the simplified model. Data fitting has never required exact modeling. And again, everything I'm saying has been validated with in-flight data. This topic ends with a procedure for setting process noise levels. The tips I want to give about integrity all involve building on the classical methods introduced originally. At first, only one biased satellite was considered. I generalized that in 1992 while also enabling fault isolation or exclusion by a parity scalar instead of requiring a vector. Later, I normalized the matrix decomposition, which provided two advantages. It replaced suboptimal nav estimates by optimized ones and also produced a dimensionless parity statistic with variance of 1. In addition, after using the established differencing across SVs to focus on nav only, I furnished closed-form solutions that account for the resulting correlations. Everything was done with nav and integrity merged together, while eliminating the restriction to the case of overdetermined solutions. In fact, the number of observations was reduced all the way down to 1. Crucially, every type of observable can be included: ELORan, pseudo-range, carrier phase, radar range, etc. Data from any source as a natural extension from tight, ultra-tight integration, keeping everything open to allow full flexibility. All of these methods give state-of-the-art performance from a low-cost IMU under severe vibration, centimeter per second velocity, and a few tenths of a milliradian leveling RMS using carrier phase without the usual risk of catastrophic error. That plus other vulnerabilities were eliminated by just using 1-second changes. All the large degradations were thereby canceled except multipath, and that one sticks out like a sore thumb, easily detectable and rejected. Even low elevation satellites can be used, all the way down to the horizon, because ionotropo propagation won't change much over 1 second. Their interoperability doesn't depend on correctness of ellipsoid models nor timing adjustments. Intermittent data can still be used even if repeatedly interrupted. Merging of integrity with nav was done for both dynamics and position. Applicability extends to all sensors. Here's a time history for the phase residuals from the flight data, with switching of the subtraction reference SV because it went below the horizon, equating the plus-minus maxima to plus-minus 3 sigma, and accounting for a couple of factors of the square root of 2 due to subtracting across 1 second and across SVs. This easily supports the conclusion of 1 centimeter per second RMS velocity accuracy. Collision avoidance is in urgent need of improvement. It was less urgent in the autumn of 2000 when I made a presentation to an RTCA SC-186 working group. My recommendations were shelved, and offered a course entitled GPS for Collision Avoidance. Almost no one attended. Advantages of the proposed changes are as massive as they are plentiful. Once again, here goes. What's needed is not instantaneous position, but future position, projected forward to the time of closest approach. And that has to be far enough in advance to allow flight path adjustments to take effect. And those path adjustments need to be more like trim commands rather than sudden lurches that leave passengers screaming. That's no exaggeration. Immediately, that makes velocity accuracy vastly more important than current position. Also recall that 3 times the RMS error is too small when 10 sigma can't be discounted. And that, after amplifying RMS velocity error by a multiplier like 10 or more, that result is squared to express the area of uncertainty at any altitude. So, instead of ADS-B's 10 meter per second, not vectorial and not relative, collision avoidance needs relative velocity accuracies of centimeters per second. Now, some good news. That performance has been achieved in a flight test at Ohio University with provisions already being commonly used. By sharing the 1-second changes in carrier phase just discussed instead of position reports that will never be adequate for collision avoidance. Here's a logical progression of the many reasons that justify what I just said. No need for me to repeat those. Just pause and read at whatever pace is suitable. The Ohio U flight test that first enabled me to validate methods described here for NAV, under the direction of Professor Frank Van Grass, was later followed by application to tracking under the direction of Professor Martin Uftehag. Centimeter per second relative velocity. It would be overstating the case to claim that everything has been settled in regard to this topic, but the comparison is jarring. A centimeter per second is 1,000 times better than 10 meters per second, and squaring that for area of uncertainty gives a factor of 1,000,000. There was a time when accurate fixes were sufficient performance criteria. Those days are over. Some or all of the features listed here are important for many applications. Purchasing a turnkey proprietary system will provide the first of these traits, but for the rest of them, little or nothing. To receive all benefits, let each subsystem contribute what it has without expanding beyond its range. A central processor can simultaneously determine every possible combination of federated and integrated solutions, plus executing decisions as to which ones should be made available under circumstances according to adopted rules. It's also been a long time since navigation data had a narrow range of utility. Once again, the preceding slide describes how to make the most of provisions and avoid being painted into a corner. Navigation and tracking haven't changed enough to capitalize on current capabilities. Nowhere nearly enough. The sheer magnitude of current challenges combined with required future improvements will demand overcoming strong resistance and breaking old habits. To the question of whether in-air scenarios should be defined by avionics or radars, the answer is both. Visualize each participant acting in classic air-to-air fashion with itself at the origin of a coordinate frame maintained and refreshed by its own central processing of all data received, with all inputs from external sources consisting exclusively of scalars, independent of and unattached to any coordinate frame. Then if one participant's frame differs from another's, that won't affect either one's perception of relative position and dynamics. Each one in its own little world, tracking squitter data from every other and treating all other participants in a consistent way according to its own worldview. Differential operation is used throughout in expressing situation awareness of each relative to all others. Crucially, the entire scheme applies also to measurements other than GNSS. Each participant can compare its own scalar measurements versus those of all others for relative nav, with differencing across all sources shared via squitter. Every individual's perception of the scenario is a three-dimensional grid, not tied to any latitude or longitude, constructed from one common collection of shared scalars, each one set of relative states controlled by whatever sources of scalar measurements it has in common with each other participant. One addition remaining to be discussed is radar. Unlike GNSS or ELA-RAN data, one user's radar measurements have independent timing, unrelated to all others. Those are not for sharing, but they don't need to be. Each participant uses radar data to adjust the origin of its own coordinate frame. In effect, an adjustment based on radar data can shift the absolute location of the entire scenario grid perceived by one user's worldview, without affecting any of the history of all other participants' relative positions. Every user does that independent of all others, while treating all others in a consistent way to maximize both thoroughness and accuracy in situation awareness. That's the concept for providing an urgently needed dramatic improvement in performance. Skeptics are invited to revisit the 1,000-fold reduction in residuals shown in an earlier slide.